next topic of the fact subject is end of line voltage support to prevent the voltage instability. This is the fourth topic of unit 3, that is the end of line voltage support to prevent the voltage instability. So before going to discuss about the voltage instability prevention method, so what is meant by voltage stability? Here we can observe that the voltage stability, that is in short form voltage stability, in short form it called as voltage stability Vs. So the voltage stability is meaning here is the ability of a system to maintain the acceptable voltages, that means minimum and maximum voltages within that. Every system have a minimum voltage and maximum voltage. Within these levels is nothing but acceptable voltages. That is the ability of the system to maintain the acceptable voltages like minimum and maximum voltages under normal and abnormal conditions. So what is meant by that? That means here we can observe that the ability of the system to maintain the voltages within acceptable limits. That means the limits are V minimum and V maximum. The limits are V minimum and V maximum. Within these limits, V minimum and V maximum under normal and abnormal conditions. So what is meant by that? That means here, if the system is working under normal conditions, it takes some voltage and that means it receives some voltage. If a fault occurs, that is means abnormal situation. Any fault, it may be open circuit fault or short circuit fault. That is nothing but abnormal situation. Under that, the voltage may be under voltage or maybe over voltage. So even though the fault occurs, that means even the normal and abnormal conditions, the voltage, the ability of the system maintain the voltage is nothing but a voltage stability. If not maintained like that in normal and abnormal conditions, then we can say that is a voltage instability. From this knowledge, we can observe that the voltage instability is one problem which is severely occurring in the power systems. So in order to prevent this voltage instability problem, generally we go for the compensation technique. So in the previous class we discussed about the midpoint voltage regulation. In that we discussed about shunt compensation. Again we studied that how the compensation can improve the active power and how the compensation can improve the real power. Similar to here, similar to the same compensation technique can also adopted here. That means ఇక్కడ కూడా మనం ఆ టెక్నిక్ని అప్లై చేస్తే ఆ వోల్టేజ్ ఇన్స్టెబిలిటీ ప్రాబ్లమ్స్ అనేవి తగ్గుతాయి. అసలు వోల్టేజ్ ఇన్స్టెబిలిటీ ప్రాబ్లమ్స్ ఎందుకు వస్తున్నాయి? దేర్ ఆర్ ఎనీ ప్రాబ్లం ఎప్పుడు వస్తాయి? నార్మల్ అండ్ అబ్నార్మల్ కండిషన్స్లో వస్తున్నాయని చెప్పుకున్నాం. నార్మల్ అబ్నార్మల్ కండిషన్లో సిస్టమ్ అనేది వోల్టేజ్ లిమిట్స్ వితిన్ లిమిట్స్లో లేకపోతే, అంటే ఏ లిమిట్స్ సిస్టమ్ యొక్క వోల్టేజ్ అనేది వితిన్ లిమిట్స్లో లేకపోతే మనకి దాన్ని ఏమన్నా వోల్టేజ్ అనేది ఇన్స్టెబిలిటీ ఉంది. అంటే వోల్టేజ్ ఏముంటుంది ఇక్కడ మనం ఏమంటున్నది వోల్టేజ్ కొలాప్స్ అయింది అంటున్నాం. సో ఇఫ్ that kind of situations occurred in a system, it leads to grid failure. Generally, always we need a constant bus voltage at the grid side. You are not able to maintain that voltage in order to due to the problem of voltage instability problem. So due to this presence of this instability problem, we are not maintaining the constant voltage at the grid level. This is nothing but a voltage instability. Then there are several causes which leads to voltage instability problem. Then generally there is a loss of some generation, or suddenly transformer tap changes and some kind of dislocations, that means connections. So for example, for sake of simplicity, let us assume that one problem occurred in the power system. For example, that problem is for example here, let us consider the one load which receives the power from two generations, generation 1 and generation 2. For example, let us assume that the load which can receive the power from both the generator 1 and 2, that means the load which consumes the power from generator 1 and 2. If it has some problem occurred in the some system, power system, suddenly the generator 2 have failure occur. Suppose if the problem occurred in the generator 2 or generator 1, whatever may be, For time being, I am assuming that generator 2 is having the problem. Therefore, generator 2 is disconnected from this load. That means entire power is which will deliver from generator 1 to load. That means generator 2 in the ideal situation. That means will not carry any power. So therefore, generator 1 is carries the power from here to load. Therefore, entire power can be bear by or carried by generator 1. Due to this, there is a voltage instability problem occurred in this load end, that means receiving end. There may be overload or may be underload situations. So this kind of situations are voltage instability issues due to the presence of one loss of generation. One loss of one generator loss of that's why any voltage instability issues అంటారు. సో జనరల్గా ఇప్పుడు కూడా బస్ దగ్గర వోల్టేజ్ కాన్స్టెంట్గా మెయింటైన్ చేయాలి. కస్ దగ్గర కాన్స్టెంట్ వోల్టేజ్ మెయింటైన్ చేయాలంటే వోల్టేజ్ ఇన్స్టెబిలిటీ ప్రాబ్లమ్స్ తీయాలి. వోల్టేజ్ ఇంప్రూవ్మెంట్ ప్రాబ్లమ్స్ రిమూవ్ చేయాలంటే వీ నీడ్ సమ్ ఎక్స్ట్రా మెథడ్. ఆ మెథడ్ని మనం కంపన్సేషన్ టెక్నిక్ అంటాం. సో బట్ హియర్ our topic is end of line voltage support to prevent. Why we are connecting the compensation technique at the end of the line? Because of in the radial transmission system, voltage stability issues, that means voltage instability issues or voltage imbalances occurs at especially in the end of the line. To prevent this voltage collapse or voltage imbalance conditions, generally in the end of the line we are connecting the one compensation device. Is it clear? So that's why in the most of the time we are connecting the compensation device near to the load end in case of radial system. Okay. So again, coming to our topic, so this is about justification of our topic. Now we are going to the one example taken as the one example to understand very clearly about this concept. So let us assume that here here having two systems, that is the one generation, and the sending end voltage is Vs and the receiving end voltage is Vr. The impedance of the load is Z. That means here generation is Vs and receiving end voltage is Vr and impedance is load Z and the transmission line reactance is X. This is one system. So in order to analyze the power flow equations in a particular this system, generally the P is nothing but V1 V2 x into sin delta and Q is nothing but U x into cos delta minus 1, which I have already seen in the previous sections. So here you can observe that from sending end to receiving end there is a transmission line, that is reactance. It carries the current, let us say that current I. It carries the current I, line current I. So in order to analyze these voltage instability, we generally we draw the PV curve. That is, we draw the PV curve. So where we getting from this concept? Generally in the power system there are three stability issues: general voltage stability, and frequency stability, angle stability. But out of which here we have discussed about the voltage stability issues. In order to analyze these voltage stability, there are two methods available in the power system. That is the PV curve method, that is the power, active power and voltage stability analysis, PV VSA method, and QV VSA method. That is the active power voltage source analysis method, voltage stability analysis method, and QV, that is the reactive power and voltage and voltage stability analysis. Where VSA is nothing but voltage stability analysis, V is nothing but voltage, P is nothing but active power, Q is nothing but reactive power, and V is nothing but voltage. So generally out of which we go for this PV method to analyze the V versus P. That is here the P is nothing but here power, that is the load power. That means the impedance which carries the power P, load power P in terms of per unit value, and VR is nothing but voltage at the receiving end, it is also in the per unit. Generally in the power system, so many times the consumer side, the receiving end side facing the voltage stability issues. That's why we concentrate on always in this receiving end only. That's the reason why P versus V curves at the receiving end were not for sending end voltage and sending end generation. We always concentrated about P, load power. Here P is nothing per unit value, especially the power is nothing but load power. The load which receives the power from the generation, that is the load power, and VR is the receiving end voltage. this curve is nothing but P versus V curve. This curve is nothing but power versus voltage curve. For time being, assume that for different load having different power factors. Generally, we go for any kind of power systems or any kind of home applications or any kind of commercial or maybe industrial applications. So many loads are there. The loads may be lagging loads or leading loads. In that, the same scenario also applicable to this large power system network. Because of large here is nothing but we have the long transmission line is about kilometers. That's why I'm represented as large here. So here we can observe that the different values of power factor, the P versus V curves are changing here. So here this is the unity power factor. This is the curve in the unity power factor, and this is 0.97. This is the 0.97 leading, and this is 0.8 leading, and this is 0.9 leading, and this is 0.85 lagging, and this is the 0.8 lagging. That means here this is the unity power factor reference, and this is the 0.85 otherwise 0.95 lagging and 0.85 lagging. This is 0.97 leading, and this is 0.9 leading. And it means this is the unity towards unity. This means the value decreases, towards unity the value increases here from lagging side. From this concept we can observe that the voltage stability decreases with inductive load, because of there are two kinds of loads in any commercial systems or industries or any home application systems. Generally the inductive loads and capacitive loads, that means lagging loads and leading loads. If the voltage stability decreases with lagging loads, that means here you can observe this is the unity power factor, this much of voltage, this is the lagging power factor, this is the voltage, this is the some kind of lagging factor. That means example for taking as 0.85, and this is 0.9 lagging, this is 1 unity. That means voltage from 1 to unity to 0.95 lagging, from 0.95 to 0.85 lagging, the voltage will be, stability will be decreases. Similarly, for leading loads, the voltage stability will be increases. From this curve, we can observe that voltage stability decreases with lagging loads, and voltage stability increases with leading loads. For sake of simplicity, capacitive loads, voltage stability increases. For inductive loads, voltage stability decreases. This is about without compensation. This is existing in any power system, generally from generating to load end. We can also clearly the curve here. That means at this power, initially for example, at power P is equal to 0. That means power into meaning P into load power. That means without any power, load power. That means you are disconnected the load simply. Without any load power, how much voltage is here? That is the VR. That is the 1 per unit. Here 1 per unit. Without any load power, the receiving end voltage is 1 per unit and the load power is 0. If you further increasing the load, that means while connecting the load, increasing the load. While increasing the load, to meet this load demand, generally the impedance offered by the load decreases. That means you are further increasing the load, but to meet this demand, generally we are reducing the impedance of the load. While reducing the impedance of the load, the current drawn by the transmission line, the current drawn by the load, or otherwise current drawn by the load, అంటే ఇండైరెక్ట్గా ఏంటి ట్రాన్స్మిషన్ లైన్ నుంచి వచ్చి కరెంట్ ఏమవుతుంది ఇక్కడ నుంచి ఇక్కడ రీస్ అవుతుంది, అంటే ఇండైరెక్ట్గా ఏమవుతుంది ఇక్కడ ఉన్న కరెంట్ ఇక్కడ ఉన్న లోడ్ కాబట్టి అందుకోసం ఏమవుతుంది ఇక్కడ కరెంట్ డ్రాన్ బై ది లోడ్. దట్ మీన్స్ వైల్ రిడ్యూసింగ్ ది ఇంపిడెన్స్ ద కరెంట్ డ్రాన్ బై ది లోడ్ increases, and in this scenario the voltage drop appears across this transmission line also increases, but very smaller rate. From no load condition to small increment in the load, the impedance offered by the load decreases, the current drawn by the system increases. As a system is consisting of transmission line and load increases, then voltage drop ante V into Ix also increases, but this is not in a faster rate. So iదే మనం ఇక్కడ కర్వ్ లో చూపించాం. If P is equal to 0 V per unit, if you are increasing the load from 0 to this one, the voltage drop decreases. It is happening. Is it clear? This point up to certain point, ఆ పాయింట్ ఏమంటారంటే ఆ సర్టెన్ పాయింట్, ఆ పాయింట్ ఎక్కడ వరకు జరుగుతుంది అంటే ఎంతవరకు అండ్ P increases, voltage decreases while decreasing the impedance, the current drawn by the load increases, therefore voltage decreases, which is up to some critical point. In some textbooks is also mentioned as nose point. In some textbooks is also mentioned as nose point. This point ఏమంటాం మనం nose point లేదా critical point అంటాం. At this point, the point represents for various kind of load and power factor, the voltage changes. This is the nothing but a critical point or nose point. Nose point అంటే ఇక్కడ ఏంటి, but various power factors and loads, the voltage changes. That is nothing but a critical point. At this point, load increases, voltage decreases up to this critical point. After that, if you further increasing the load, the impedance will be further reduces. The impedance will be further reduces. The current drawn by will be again more, and the incremental increase the voltage drop will be. That means voltage drop ఏదైతే వస్తుందో ఆ voltage drop అనేది ఫాస్ట్గా మనకి ఇంక్రీజ్ అవుతుంది. ఫర్దర్ రిడ్యూసింగ్ ది ఇంపిడెన్స్ టు ఎందుకు రిడ్యూస్ చేస్తాం, టు నాట్ టు మీట్ ది లోడ్ డిమాండ్ పెరుగుతుంది కాబట్టి మనం ఏం చేయాలి, ఇక్కడ కరెంట్ ఎక్కువ సప్లై చేయాలి. కరెంట్ ఎక్కువ సప్లై చేయాలి ఎందుకు, వోల్టేజ్ అనేది ఎప్పుడు కూడా బస్ దగ్గర కాన్స్టెంట్గా ఉంటుంది. ఇక్కడ ఇప్పుడు మనం కరెంట్ ఎక్కువ సప్లై చేస్తే ఏమవుతుంది, ఆటోమేటిక్గా మనకి ఎక్కువ పవర్ డ్రా చేసుకుంటుంది. ఎక్కువ పవర్ డ్రా చేసుకోవాలి, కరెంట్ ఎక్కువ సప్లై చేయాలంటే obviously we are reducing the impedance. While reducing the impedance, definitely the voltage drop increases here. So if you further increasing the load, if further voltage drop rate will be faster rate. That means voltage drop అనేది fast గా increase అయిపోతుంది. So increase అయిపోయిన voltage అనేది sudden గా increase. That means when increasing the load, the voltage drop will be faster rate at a particular. Similarly, all kind of different load power factors, this is happened same. So this is about up to critical point, the voltage drop will be slowly decreases. After critical point, voltage drops increases very faster rate. This is about the voltage P versus V curve. We will continue with the next topic. That means continue the next topic with the help of the compensation dividers in the next section.